Now let's introduce the general method. Of course, we do not always have this luxury where the left-hand side of our linear differential equation is immediately written in the form where it is just the derivative of the product of two functions. But a very neat trick allows us to always be able to transform it into this form. Right, so the idea is that we want to multiply our whole equation by some unknown function mu of t, which is called the integrating factor, to ensure that the left-hand side is just as we want it to be. Right, so what happens if we multiply the whole equation by mu of t? So then the left-hand side becomes mu y prime plus mu p y. Now I'm skipping of t, so I hope it's alright. Now instead of g of t, the right hand side became q of t. Well, I hope it's not a big deal either. So mu q. Okay. Now we at the same time we want the left hand side to be the derivative of mu times y. But if we write it down, applying the chain rule, then we would get mu y prime plus mu prime y, right? Mu prime y. Right, so this whole thing should be equal to this whole thing. So let's just mention that mu y prime here and here we have. Then the rest is mu p y equals mu prime y. Of course, y and y cancels out, so the remaining part is just mu p equals mu prime. So mu p equals mu prime. Or we can interpret this in terms of as a differential equation in its own right. Right? So let me rewrite it as a proper differential equation. So this is d mu dt equals p of t times mu. So where p is a certain specific expression of t, so that comes from the original differential equation. Well, but this is a separable equation on mu that we can solve, so let us do it. D mu over mu equals p of t dt. So then we need to integrate, and the antiderivative of d mu over mu is logarithm of absolute value of mu, and this would be, well, since we don't know what p of t is, we cannot really change it, so it should be just the antiderivative of p of t dt. But now notice one more thing, that our purpose now is just to find one particular integrating factor. We do not have to know all of them. So in other words, instead of solving this differential equation in the most generality, we are only concerned now with finding any particular solution. So anything, anyone will do. So in particular, it may have a positive solution and a negative solution, but we don't care. So if we are able to find a positive solution, it's already enough. So in other words, we don't really have to care about possible negative solutions. So then we apply the exponential function, and then we get that mu is e to the power integral of p of t dt. So, and again, an alternative would be minus the same thing, but we don't care because we don't have to find all solutions now. Alright, so now I have just rewritten. So the first step of solution of a linear differential equation is to multiply it by this integrating factor. And so once again we need to take p of t, integrate it, and then we raise e to this power. And then the left hand side, according to the construction, is going to be mu of t times y everything prime. But then we can think of this as a differential equation with the unknown mu of t times y. And then it tells us that the derivative of the unknown function is mu of t times q of t, which is just, which means that the general solution is the antiderivative. So notice one more thing, is that when we find the integrating factor, we do not have to find all possible integrating factors, which means that here plus c is not really needed, because changing this plus c, we will be able to find more different suitable integrating factors which we don't really need. But here plus c is important. So here plus c is important because it allows us to find all possible solutions of the differential equation.